Now it is your turn. Let's build and stress this chapter's operations in C. Time for Lab 1. Your objective is to build the full core of disjoint set union in C. Make set, find set with path compression, and union sets by rank. Then prove they all agree with each other. You will implement 4 functions. First, make set. It takes the parent array, the rank array, and n, and starts everyone in their own group. Second, find set. It takes the parent array and an element x, walks up to the root, and flattens the path with path compression along the way. Third, union sets. It takes both arrays and 2 elements, x and y, and merges their groups by rank. Fourth, same set. It returns true when x and y share a root, when find set of x is equal to find set of y. To test it, start with 8 elements. Before any union, same set of 0 and 1 is false. Then union a few pairs and recheck the answers. For example, after joining 0, 1, and 2, same set of 0 and 2 should be true. One hint: same set needs no logic of its own. It just calls find set on both arguments and compares the 2 roots. Give it a try before you look at the solution. Let's look at the solution. This is same set. It takes the parent array and 2 elements, x and y. It returns find set of parent, and x is equal to find set of parent, and y same root means same group. That is the whole function. Now the output, 0 and 1 same set, 0. They start apart, so the answer is false. 0 and 2 same set, 1. After the unions, they landed in the same group. 0 and 3 same set, 0. Those 2 groups were still separate at that point. 5 and 7 same set, 1. The chain of unions joined them. 0 and 4 same set, 1. After the last union, both groups merged into 1. And remaining sets, 2. Everything collapsed down to just 2 groups. Make set, find set, and union sets are unchanged from the chapter body. Time for Lab 2. This one is about counting. Your objective is to use disjoint set union on a graph's edge list to do 2 things at once. Count the connected components and flag every edge that closes a cycle. Both come from one simple rule. Take the edges one at a time. If find of u is equal to find of v, the 2 ends are already connected, so this edge closes a cycle. Otherwise, it joins 2 components, so you call union of u and v. The test graph has 6 vertices. Edges 0, 1, 1, 2, and 2, 0 make a triangle. Then edge 3, 4 joins another pair, and vertex 5 sits alone. Before you run it, try to predict. The triangle has 3 edges, but it only needs 2 to connect all of 0, 1, and 2, so the 3rd edge must close a cycle. How many components remain in total, counting the lonely vertex 5? Give it a try. Let's look at the solution. The loop walks every edge, one at a time. It reads the 2 endpoints of this edge into u and v. Then the key test. Is find set of u equal to find set of v? Are the 2 ends already in the same group? If yes, this edge closes a cycle, so it increases cycles by 1. If no, the 2 ends are in different groups, so it calls union sets to join them. Now the output. Edge 0, 1 connects 2 components. Edge 1, 2 connects 2 components as well. Edge 2, 0 closes a cycle. Its 2 ends were already linked through the triangle. Edge 3, 4 connects 2 components. Connected components 3. Cycle closing edges 1. The 3 groups are 0, 1, 2, 3, 4, and 5 all alone. Time for Lab 3, the challenge. Your objective is to build a minimum spanning tree with Kruskal's algorithm. You sort all the edges by weight, then add each one that does not close a cycle. Chapter 16 named this algorithm but could not implement it there because it needs the disjoint set union you just built. The pseudocode is short. First, make a set for every vertex. Then sort the edges by weight from smallest to largest. Then walk the edges in order. For each edge u, v, if find set of u is not equal to find set of v, adding it cannot close a cycle, so take the edge and union the two ends. Stop once you have taken n-1 edges. Now implement it in C-sort a fixed edge list with Q-sort. Then walk it in order, applying exactly the Lab 2 rule. If the endpoints are in different sets, take the edge and union them. If they are in the same set, skip it, and stop once n-1 edges have been taken. One tip that matters for reproducibility. Break sort ties by comparing U and V as well as the weight. Q-sort stability is unspecified, so two equal weight edges could otherwise produce different spanning trees on different runs. Both would be valid, but they would not be reproducible. Pause and give it a try. Let's look at the solution. First, Q-sort orders the edges by weight, from smallest to largest, breaking ties on the endpoints. The loop walks the sorted edges, and it stops early, as soon as MSD edges reaches V-1, a full spanning tree. For each edge it tests, is find set of U not equal to find set of V? Are the two ends in different groups? If yes, it takes the edge and unions the two ends. It adds this edge's weight W to the running MST weight. And it increases MST edges by 1, counting the edge we just took. Here is the run. The cheapest edge, 1 to 2 with weight 2, is taken first. Then 3 to 4, also weight 2. Then 4 to 5, weight 3. Then 0 to 1, weight 4. And here is the interesting line. 0 to 2, also weight 4, is skipped because it would close a cycle. 0 and 2 are already connected through 1. That single skip is the whole reason Kruskal needs this chapter structure. Then 1 to 3, weight 5. That is the fifth and last edge we need. 5 edges taken, total weight 16. 6 vertices need exactly 5 edges for a spanning tree, so the loop stops as soon as it has them, and the 3 most expensive edges are never even examined.